for today. Thanks everybody for joining. We're joined today by Dr. Scott King, who's out of our geosciences, or is it geosciences, geophysicists?
Geoscience.
Okay, yeah, I've heard it's the geoscience department, but you're a geophysicist professor?
Yes.
Or is that the
Yeah,
gray boring
exactly.
of everything? And is going to join us today and talking about what's going on, and I love your title, which is not here, of what's shaking on Mars. So we'll, without further ado, go ahead and take it.
Okay. Well, looks like my pointer will work, so maybe I will kind of stay seated and work with that.
Yeah,
but
totally fine.
it's always fun to be able to talk about what's going on with the InSight mission. I am a guest investigator on the mission, and that means I joined the mission about 6 months before landing. It had already launched, so I missed the launch, and unlike some of the other people, I had not been around for the building of the hardware and all of that sort of stuff. I was added on at the end of the, before the landing. And so I did get the thrill of experiencing the 7 minutes when there's a communication blackout. And since it's about 7 minutes for information to get from Mars to Earth at that point, as soon as the communication blackout happened, we realized it either landed successfully or crashed, and we won't know for 7 minutes. But it did land successfully and has been operating successfully on Mars since November 26th of 2018. So coming up very closely on another Earth year anniversary. So there have been a lot of previous missions to Mars. People are very familiar with a lot of the rover missions, going all the way back to the ancient days of the little Sojourner rover in 1997, to things like Curiosity and Perseverance, which are about the size of a small car, roving around Mars. And people have probably paid attention to the drone, the rotocopter Ingenuity, which is a tech demonstration that you can see down there. And so we have a lot of experience with instrumentation on Mars. We know a lot about the surface of Mars, but we don't know so much about the interior. We still have a lot of very basic questions about the interior structure of Mars. And really what we're trying to test are assumptions that everyone makes in planetary science, that all of the rocky planets form out of the same material. And we really want to know how these have changed over the past 4.5 billion years. We really, surprisingly, as much as we've studied Mars, we really didn't understand just how big the core of Mars is. It could have been fairly small, which would have changed some of the dynamics of the rocky interior that I study. Turns out it's much bigger. It's in proportion, it's similar in size to Earth's core, which is not exactly what we had expected. And so the questions of how these planets have evolved really gets down to being able to test, did all of the planets form from the same material, or were there different reservoirs of material that different planets formed out of? So basically our understanding is that planets form by collisions of smaller objects colliding together. Those smaller objects that collide together produce a lot of heat. That heat in turn often is, once the planet gets to a significant size, is enough to melt the planet. And differentiate the iron core from the more rocky mantle and the less dense, more volatile rich crust. And so we know that this structure forms. We expect this structure on all these planets. And so we expect it on Mars, but there were a lot of things we really didn't know enough of the details to be able to test some very specific assumptions about how the inner solar planets formed. So we think we know Earth pretty well. We've had 100 years of seismology. Seismometers have been on the Earth. The core was discovered in 1906. The inner core was discovered in the 1940s. And so we've developed up quite an understanding of the structure of the interior over the past 100 years, using largely seismology, but also using space geodesy and an awful lot of information from geology and so forth. We had seismometers on the Apollo mission. You'll see how difficult it is for a robot to deploy a seismometer. The astronauts just literally took them and set them on the surface. And it was, we always, in my intro classes, always say, you know, anything a human can do, a robot can do. We don't need to send humans. It's very dangerous. It's very expensive. But when you kind of see how difficult it was to set a seismometer on Mars, you kind of realize that, that may be stretching it a little bit. But we had almost 8 years of seismometers operating on the moon. We have rock samples from the moon. We know a lot about lunar quakes, and I'll show you the difference between the shaking from a lunar event and the shaking from a Martian event and an Earth event. They each kind of have their own distinct flavor, and we're still trying to understand some of how that comes about. But the interesting thing about Mars is it's sort of in between size. It fills a gap between an object that's as small as the moon, which for the most part is very brittle, very cold, and all the activity that geologists are interested in, you know, happened 2.5, 3 billion years ago, to, you know, something on Earth where you have active tectonic events today, where you have volcanoes today, and so forth. And so Mars sort of sits in the middle, and being intermediate in size, it's probably lost its heat, a lot of its heat, a lot earlier than Earth has, but it still retains more than the moon. So it gives us an in-between size of an object to work at. And the sort of the nominal way that the mission has been described, especially with the non-scientific community, is that we're giving Mars a checkup, right? When you go to the doctor, you get your pulse measured, you take your temperature, and they, you know, bang your knee for some reason to check your reflexes. I can understand the first two. I don't quite understand why the reflexes, other than it's kind of fun to do and bang on somebody. But anyway, so the sort of the equivalent of this, in a sense, is that of the pulse of the planet is Mars quakes. And you'll also see seismometers should be able to pick up impacts. And we have some questions about whether some of the signals we see might actually be impacts. And that's still an area of active discussion. And we have a heat flow probe, so we're going to measure the temperature. We're going to get an estimate at one point. We have heat flow measurements from the moon, but we don't have heat flow measurements from any other planet other than Earth. So we'll look at those. And then all of the rotations and the wobbles that the planet undergoes as it's spinning, can be used to tell about the internal structure. I'm not really going to talk about that part today, but it feeds into a lot of the results that we have obtained and provides sort of a different complementary measure of the size of the core and the material properties of the core. So these are the things that we're going to look at. And missions always, in order to sell it to NASA, you have to list these science goals. The science goals for InSight determine the size of the core. I'll show you that today. We have a pretty good answer on that now, as well as an uncertainty. The composition of the core and its state. Is the core solid? Is the core liquid? Or is the core somewhere in between? Turns out if the core was solid, the planet would be so cold that some of our other things, you could almost rule out the core being solid before you even began. But it's nice to be able to confirm with measurements. The thickness and the structure of the crust. Well, we have one seismometer, so we're going to be able to get information right underneath the InSight seismometer. But we can use gravity to essentially map the rest of the planet, constrained by what we know about the thickness from InSight. The structure of the mantle, the rocky interior of the planet, and where the materials change properties, they change at diagnostic pressures. And so that tells us something about, we can see where that change occurs. We know that pressure, that can tell us something about the temperature. We can work back and forth to gain information there. And with the heat flow measurement, we're going to figure out how warm the interior is and how much Mars is cooled. And this relates to the major heat source, other than the formation of the planet, is the development or the decay of radiogenic elements. And so by estimating where Mars is in its cooling progression, we can work backwards and figure out the distribution of radiogenic elements, which again tells us something about how material is segregated across the inner part of the solar system. So there are three main instruments. The seismometer is called SEIS. I forget exactly what the acronym is. The rotational inertia determination is from some antennas called RISE. They are actually tracking the location of the InSight lander on Mars from Earth using Doppler shift to within several centimeters. And they're tracking this through time, and that change in properties tells them something about how Mars is density is distributed. The seismometer, turns out seismometers are so sensitive. Essentially, it blows my mind, because the instrument people say it can measure deformation on the order of angstroms, which I find, how can you even conceive of this? But a more useful measure to me is if I were standing a kilometer away from InSight and jumped up and down, it could determine that my mass jumping up, and I've got more mass than I need, but it would be able to determine that I had been jumping up and down. It's got that kind of sensitivity, which is typical of the best seismometers we have on Earth. So it's equivalent in some ways to the very best seismometers we have on Earth. On Earth, we get around some of the problems that we have on Mars by burying them in vaults. We have a very nice seismometer that's Virginia Tech that's out by the airport. It's not clear to me with the airport extension that it's still, I think it still exists, but it's, we have that. And then we have the heat flow measurement from this instrument called HPQ, the heat flow and physical properties package. We'll talk more about that. That's a very interesting part of the mission. Interesting because actually it didn't work as expected. But here's the instrumentation in the artist's image. And you can see not only do we have the seismometer, which has to get from the deck of the lander to the ground, and this HP cubed instrument, which has to get to the deck from the deck of the lander to the ground. We have these antennas called RISE. We have a UHF antenna that actually communicates with the Odyssey and Maven spacecraft. Because other than RISE sending signals back to Earth, the spacecraft is not communicating directly the data to Earth. The data is beamed back to the orbiting spacecraft, and they send it back to Earth in a relay method. That may create some very interesting issues because the spacecraft are only overhead a couple times a day. You can only send commands down or uplink data during that period of time, so that it makes working very asynchronous. There's also a magnetometer, which I don't think is shown up on here. There's some cameras. There's this deployment arm, which becomes very important in understanding what's going on. And there's temperature, wind, and pressure as well. In a lot of ways, we have these, and you'll be able to see that because seismometers can basically, they're really good. In some ways, people have said seismometers are really good at sensing anything other than earthquakes. They sense changes in pressure. They sense the wind is a big factor. So anytime we have something that looks like a seismic event, it's nice to be able to look at the pressure and temperature, everything else, and make sure there's not some sort of atmospheric disturbance going on at the same time. So just for some context, this is from the weather station. This is one particular day, just to give you a sense of what's going on. The purple curve here is from the twins, the atmospheric measurement on top of the spacecraft. And you can see during a one-day diurnal cycle, it's going from -100 C to -20 C. Plays havoc with any kind of electronics and anything like that. So the curves that you see that look a little bit shifted in time, but still are diurnal in nature, are from the sensors within the seismometer itself, under the windshield with the heater on and everything else. And you can see that that's within the tolerance of what they're able to measure at. You can see the weather on Mars. This is a 3 or 4. A day on Mars is called a sol. Day on Mars is 24 hours, 39 minutes and change. And so it's called a sol. The mission starts by definition at sol 0. And so time is counted, local time is shown here. And you can see this is for 3 revolutions, 3 sols. And you can see this really repeatable cycle, both in the air temperature, which is the top curve, the pressure, which is the intermediate curve, and the wind direction and wind speeds, which the winds quiet down quite a bit during the evening. they're, ranging from a few meters a second to as 10 meters a second or so. Very consistent direction, which is as best we can, the atmospheric people on the mission have determined is essentially due to the slope, which I will show you, this very large grade change in elevation. It's almost like a katabatic wind or something like that, daily and nightly off of the instrument. So the sol is, this is after we landed, take images of everything, figure out where the rocks are. You can't put a seismometer on the rock. You have to have a nice level place. So actually they chose the landing site to essentially be the most geologically boring site they could think of, because seismometers like geologically boring sites. And so they're putting the heat shield, the seismometer down, then putting the heat shield down after they've chosen the location and scoped everything out, checked out the instrumentation and made sure that everything is working as expected. And as you can see, things progress very slowly, because before you let go of the grapple and set the seismometer down, you want to make sure that it's right where you think it's going to be. So you take a picture, you have to beam that picture back up to Odyssey. It comes back to Earth the next day or the next 6 hours. Okay, we like where it is, let go. It's kind of amazing, the process. So this took almost 50 days to get the seismometer down and the windshields down. And you can see in the sequence of images from this camera, the seismometer's down, the tether's there, they blow a little bolt because the tether itself is a pretty stiff object and you don't want thermal contraction pulling on the seismometer. So they actually have a little wire gap loop in order to separate, and they're pulling the tether away now that they've blown the bolt for that wire gap loop. And then the wind and thermal shield goes down on top of the seismometer. Interesting thing, which you don't necessarily think of, if you're not an instrument person, which I am definitely not, looked like this little pattern up here is just like some kind of pretty little design or something like that on top of the seismometer. Serves a very useful purpose. Seismometers want to measure, essentially any seismometer like this is 3 instruments. One that measures vertical, one that measures north-south, one that measures east-west. So you have to know when you put it down, where's north, where's whatever. That's essentially a sundial. And they use the shadow and the time of day and everything else to determine exactly how the seismometer was oriented. They know exactly where the things are within the element itself here, and they can orient everything exactly the way they expect it to be oriented. There's the heat shield down on top of it. Picture, everybody's happy. It's leveled and ready to go. So if you've used to seeing seismic waves and pictures like this, and this is what I was used to seeing, you'll see that an InSight mission, the seismologists look at things a little bit differently. And it was kind of difficult to wrap my head around at first when you saw it, but typically, how do you tell how far away you are from something? When the earthquake happens, energy radiates out in 3 dimensions, right? And then seismometers draw these lines, they call them rays, that represent the path that the energy took between the source and the seismic station. And there's energy that travels within the solid part of the body. There's energy that travels along the surface. The waves come in at different times. If you know the material properties of the structure, the difference between the time that these come in tell you how far you are from the earthquake. You have to get a little fancier. If you have only one station, the energy radiates out in certain patterns, and you can use the amplitude of these different things to say where you are in this pattern and work out where this thing had to have come from. You know, your introductory geology class will teach you that you need 3 seismometers to locate an earthquake. And in general, that's true, but you can do better if you're clever. So this is what earthquakes, moonquakes, and Marsquakes look like. And notice the scale. Time is in seconds. Looks like I've cut off the vertical scale here, but that's not particularly exciting for what we're looking at. Notice that when there's some sort of seismic event on Mars, the moon, or on the moon rings forever. The moon is very cold, it has very low attenuation, and so the energy just keeps vibrating and vibrating and vibrating. This is in seconds. So 2,400 seconds after this event happens. This is an earthquake in, I'm not sure where it is, but it's being recorded in central France. The seismometer was developed in France. So this is recorded in the Pyrenees, which is very cold crystalline rock, not unlike the area around us in some ways. And so you can see in hundreds of seconds that energy is gone. Where did my little pointer go? Thank you. Hundreds of seconds that energy goes away, and you get these 2 pulses, one of which you can relate to the P and the S. Volcanic events show up on a seismometer, something like this. Some of the energy that we're seeing could potentially be volcanic. That's, some of us wrote a paper on that. Not everyone on the team agrees, but it's there's a characteristic as lava is essentially moving up the pipe internal of the volcano. There's a sort of characteristic frequency and so forth that depends on the geometry of the ascending pipe of magma, and we think that that's what we're seeing some on Mars. 2 different Mars quakes, one that's fairly near the lander, that's 128. That means it occurred on day 128. The A means it was the first one that day. There aren't too many days where we have multiple events, but there are some, so most of them are an A. And this one is an event on Sol 173 that's further away. Again, using the, you can see now the scale here up to 1,500 seconds, down here up to 500 seconds. So it's longer duration than the Earth, but definitely shorter than the moon. And so there's distinctive differences that you can see between events on Mars, events on the moon, and events on Earth. This is one particular event, and we see these sorts of plots all the time. This takes a bit of time to work through. The 3 dark lines in the middle are time series of the broadband seismometer. Z means the vertical, N means north, E means east. So these are the 3 components of the broadband seismometer, and you can see where the seismologists have picked the P and the S wave. The very top, what you're seeing is a 24-hour record of the frequency. This is a periodogram or information like this. Very characteristic during the day, it gets windier on Mars, and that shows up in the periodograms. The event is this funny little thing right here. Some of these horizontal lines that don't seem to move throughout the day, those are lander modes. They've actually tested, and needed to obviously, but tested the shaking of the lander, and they know exactly the frequencies that the solar panels vibrate at and so forth, and they see those. And they don't really disappear, and they don't really change throughout the day, even with that large change in temperature. And so this funny little blip right here in the periodogram is the earthquake. And they blow up this part of the periodogram. This is roughly what, an hour? No. Yeah, close to an hour's worth of signal, looking at the different frequency contents. And right in where I have my arrow pointing is where you see this change in energy that is consistent with this earthquake down here. They're also looking at the pressure during this time period. They're looking at the wind direction and wind speed, and looking at the magnetometer essentially for anything else to show that this would not be something tectonic from the ground, but it might be a wind event or a dust devil or something like that. But there's no obvious changes in here. You can actually see where the magnetometer picks up some of the UHF communications. They also look and make sure that the lander arm isn't moving during this time, and that there's no other spacecraft things going on. So it's basically look at everything you can look at, and then if you can't explain it by something else, it's an earthquake, a Marsquake. So this is taking those periodograms. This is a 24-hour day or 24-hour and 39-minute sol in length. This is each sol shown here. So this is the periodogram for one sol spread out incredibly thin. And this is the entire mission's data. And you can see the seasonal effects show up really well. You can see here's local sunrise and local sunset. During the day, it gets a lot windier. And in fact, during the day, a lot of the little events that we see here, the different symbols are different types of seismic events. The colors are how confident we are of them. The brown or gray basically mean we see something pretty unusual there. We think it's tectonic, but there's almost no way we're going to get any more information out of it than that. C, we get pretty decent information, but maybe not very good control on direction. The B and A are sort of the best quality events, and you can see some of the largest events. In fact, one of the largest events was just occurred a couple of weeks ago, and you can even see those in the windy part of the day. So also see a seasonal effect when you get to winter. the winds are not only during the day, but they're also during the night, and it gets harder to see things. I should say most of what we're seeing in these really small events, you would never be able to see anything like that on Earth. There is so much cultural noise on Earth. You have, believe it or not, ocean waves and things like that causing a lot of signal disturbance, everything else. There's no way that you would even, so we're interpreting things that we couldn't even begin to see on Earth. But here's the largest events. Here's a plot. Insight is here. Olympus Mons, the largest volcano in the solar system. These three large volcanoes, Tharsis Montes. This region here is all elevated topography and volcanic construction. And you can see this is the best identified and largest events that we have. So most of them are within a 20-degree angle of the lander. A few further out, this particular region is a region called Severus Bosai, which is a fascinating region on Mars because it's where some of the most recent volcanism is. It's also where water outflows, channel outflows have been observed that are thought to be related to the volcanic activity. You see faults all over Mars, so that's not a problem. These most recent events are really important because they're the first things we've seen that are from the other hemisphere, which means they had to be larger and but also probably occurred at a time when the wind was low enough that we were still able to recover it. And these are kind of a real active, ongoing debate. So, thickness of the crust. I'll try not to get bogged down in the way we determine this, but as energy comes in and it meets a change in material properties, the seismic energies coming in, it can be deflected by the material property, and it can then bounce off the surface, bounce back off of this change in material properties and get to the station. And so you can get energy following any one of these sort of crazy paths. If you take the signal, the time series, and you deconvolve it, you can get pulses that tell you about this different energy as though it was all coming in vertically, and you can work out how these different structures form. This is called receiver function analysis. And when you stack these things together and you deconvolve them, you can see these peaks tell you you're getting reflections of energies at very characteristic points. And the fact that everything lines up like this is pretty good confirmation that you've got a nice flat line, regular structure. And so the thickness of the Martian crust under the InSight lander is about 40 kilometers, which is not terribly different from the thickness of the crust under us in Blacksburg. It's just divided into three distinct layers, and seismologists can tell us the wave speed, but they can't really tell us what the material is. And so we can make our best guesses. But this lower 20 kilometers is a little bit slower than the kind of material that would be under us in Blacksburg. It's not terribly unusual in that sense. As you get closer to the surface, the material gets slower, and the interpretation is you've got more fractured material with pore spaces and less consolidated signal. The detection of the core, essentially, here's these events in the Cerveris Fossae region. Here's the InSight lander. Some of this energy is coming essentially directly from the events. Some of this energy radiates almost straight downward, reflects off the core, and then radiates back to the InSight lander. This is called an SEIS reflection. But if you know the seismic structure, you know what time you should expect that material. And so here is one particular seismogram. This blue line is the envelope of the energy. And then these are various periodograms from other similar events. They're all lined up about the time of this peak energy. And what you can see is the triangles are where the seismologists pick this SCS phase. And this is how they determine where the core is. When you stack all this stuff and you look at the envelope of the energy, you can see a pretty consistent peak, and it's right there where we expect that to be. And so that gives us a core that's 1,830 to 1,850 or so kilometers below the surface, and a very low core density. So there has to be a lot of sulfur or some other light element in this as well. Now we get to the heat flow part of this, and we get closer to where the work that our group is doing. The idea of heat flow is really simple to measure. You measure temperature at two different known distances. That gives you change in temperature as a function of depth. You measure the thermal conductivity, that gives you heat flow. It's sort of amazing how primitive it is. We could make models of the heat flow and how it varies at the surface, but we have absolutely no ground truth. And so at least having one, and this model looks very much like the topography of Mars, and that's because the heat flow is going to be very strongly correlated with the crustal thickness, and so that shows up like this. If we have the data point here, then we can kind of constrain this whole model. So that's where this instrument comes in, the physical properties, heat flow and physical properties package. It's basically a nail or a self-hammering long structure like this that's wrapped in heater coils wrapped around it, so we can heat up the interior, watch it cool, and measure thermal conductivity. This ribbon behind it has a whole bunch of sensors in it to measure temperature changing as a function of time. And it's supposed to hammer itself into the material. This characteristic housing here is just that. That's the housing structure. The instrument is all contained in this little pile here. So the idea is that this thing hammers itself into the ground. It puts out like something like 100 newtons of force with every stroke downward. And it is assuming that there will be enough coherence of the material to stop the recoil, which is something like 6 newtons. And that's not very much, but this has been part of the problem. What you're seeing here is totally off the rails. When it was determined that the mole was not going down like it should, it made a decision to take the housing off and look at what was going on. This was not designed to be done as part of the mission. Everything that was done here was kind of flying by the seat of the pants engineering from millions of miles away with this huge time delay. So what you can see is this crater. And what has happened is the material is so loosely consolidated or unconsolidated that the hammering of the mole has essentially just compacted the material and created this huge hole, and there is nothing to stop the recoil. All right? This never happened in the test bed. I mean, everybody who sees this is like, oh, didn't they test this thing? Well, you know, as you guys who develop instruments know, yes, they tested it. They tested it multiple times. And I mean, Mars is doing something we never have seen before. So they made a decision that they would use the arm to press down on the material and try and compact everything, right? It's truly amazing that, you know, that they're not able to see doing this, right? And so they have to blindly set this thing down and compress it as close to the mole as possible, you know, completely. Everything that's done before gets done on Mars, there's an identical set of instruments in a sandbox somewhere in Altadena, probably where they faked the Apollo landings. You didn't hear me say that. And so everything is done on Earth first, but then the commands are uploaded and we wait. They actually got to the point where they put the arm right on the edge of the mole, right here, and pushed down. And the fact that they could do that because they didn't want to put the arm on top of the tether and risk breaking the tether, the fact that they had that kind of fidelity that they could, you know, to within centimeters, because this is like a couple centimeters across. The fact that they could put the arm in that exact place is just beyond amazing. I mean, so they did this compression, and what happens? Instead of going down, the mole is backing out of the hole. Thankfully, it didn't go all the way out and fall down because there was no way to pick it up again. That would have been game over. But through a very large number of tests, they were finally able to get the mole at least below the surface. They were never able to get it. The idea was to get it deep enough to go over this day-night diurnal cycling so that you don't have the temperature variation due to this, you know, the day-night cycle. So we were invited at one of the first meetings by the team, and they said, you know, there's this solution for the infinite cylinder in Parslaw and Jaeger. Why don't you guys look at that and see? We have this very fancy COMSOL solution. And so it turns out, you know, it's just the heat equation in a cylinder. You solve it, and then there's this function that at long time is of order 1, and you can relate the temperature directly to the known heat input and the thermal properties of the material. And so you can get this back out. Josh coded this up. They did 4 of these active heating experiments, and this is his results from the Parslaw and Jaeger solution. They look fantastic to me. They are slightly about 10% larger than the finite cylinder solution that was done by COMSOL. And what puzzles me still about this is the theory says they shouldn't even be this good. And in fact, in Sol 384, the mole is not even completely buried. and we're still getting a pretty good result, almost identical to what we're getting later. And so it's amazing to me that it's working, but I still don't understand why, other than to say that, you know, we don't have the right a finite length cylinder, and the fact that our cylinder is shorter than it should have been for the theory to hold. Consider the other part of our work, Josh's work, is we're trying to understand this volcanic activity. This is a topographic map of Mars. The southern hemisphere is very thick, very high elevation crust. Northern hemisphere, very low elevation crust, with these two main volcanic provenances, Tharsis, and basically everything in this circle is a huge amount of outpouring of volcanic material. Olympus Mons is the largest solar volcano in the solar system, something like 25 kilometers high. But Elysium over here, which is often forgotten, would be the biggest volcanic structure on Earth by far. The biggest one that we have right now might be the Siberian Traps or the Anton Java Plateau. Elysium is bigger than that. So the only reason people forget about it is because it's on Mars and it's dwarfed by Tharsis. But there are two of these things, and they're kind of in this place where they're very near the transition between the very thick and the very thin crust. And so understanding the interior, which is kind of what I do, and we're trying to model this and understand the thermal structure. So what here you're looking at in temperature, in color, are temperature variations. You're seeing a very cold crust and a plume of hot material with the white material in here where it's hot enough to generate melt. And so this is a calculation from my friend Walter Kiefer and his student that looks at melting and trying to understand how you create this volcanic activity on Mars. So we're doing three-dimensional modeling with a code that we use at ARC that's got something like 12 cubes of 64 pasted together to make up this sphere. We use the core radius constraint that we have. We use a complex rheology, which is appropriate for silicate planetary interiors, the same kind of rheology we use for Earth. We allow the core to essentially cool, and so the temperature at the boundary between the core and the mantle is set by the heat flow. Essentially, the core is vigorously convecting, and it basically gets as much heat out as the mantle will let it. And so we basically have a balance of these things. And we have decaying radiogenic heating, where we put some of this heating in the crust, which is expected because these large radiogenic elements don't fit into silicate materials. So as soon as anything melts, those things go. So just to show you one of these models, here we have the colors. You're seeing these oranges to golds are telling you something about the rheology of the material. It's stiffer at the very bottom of the box. It's also stiff in the lithosphere. The blue and yellow colors are going to show you temperature. What you're going to see is one mighty plume come up, and it comes up exactly where we expect it to, under the middle of the thick hemisphere. Essentially, it would be coming up under the equivalent of the South Pole. And so this mechanism is well understood and so forth, but this is not going to give us the volcanic provinces that we see. And so this is sort of things Josh is going to explain to me before he finishes his PhD, is why this volcanic activity largely is constrained to these two particular regions. Even though most of Tharsis was built about 3 billion years ago, there are some evidence for volcanic flows on a couple of those volcanoes that are less than 2 million years old, which geologically speaking means they could erupt anytime. I'm not predicting any eruptions. I'm just stating that, I mean, there's some dribble of volcanic activity within Mars, and it would be rather bizarre if it just stopped at the period in, you know, the solar system's history where we could observe it. I mean, so anyway, what is this heat source and what are these going on? So this is the kind of things that we're trying to address. So I know I'm kind of out of time and maybe gone a little bit long. I appreciate your patience, but the summary, we know that Mars has a lot of seismic activity. What is a lot? It's not dissimilar to the level and sort of size distribution that you would see on the eastern United States. It's a lot less than the West Coast, but of course, you know, the San Andreas Fault and all the plate boundaries there, Mars doesn't have plate tectonics. So there were people who were not even convinced we would see this much activity. We've constrained the size and density of the core, which was one of the first order goals of InSight. We've constrained the thickness and some of the properties of the Martian crust. That was another goal of InSight. There's a group right now looking at some of those smaller events that are trying to see whether in fact they may well be impacts. And we have a model for how many impacts we expect on Mars a year and so forth. And impacts look just different enough from earthquakes that we think we might be able to tease out that difference. So a lot of work is going on. Dust is accumulating on the solar panels, so power is continuing to go down. The best estimate is that we will lose the lander sometime this summer or something like that. There was a hope that dust devils would clean off the solar panels. They have on many of the other missions that have relied on solar panels. That doesn't seem to have happened yet. There's no reason. There have been some clever things where they've actually dropped sand on the solar panels and the sand blew away some of the dust and created an increase in the amount of available energy to the solar panel. They're weighing doing that because doing that requires energy from the arm that takes away from other things, and the energy balance is a challenge right now. Thank you. And I'm happy to take any questions that anybody's got.
So yeah, any questions there online or anybody feel free to jump in here.
Hey Scott, this is Scott. Thank you for that very interesting talk. One thing that had me curious, it sounded like there's more of a liquid core than I thought at Mars. You know, it sounded pretty big, and I was curious. I thought the lack of a magnetic field meant there was no significant liquid core.
Well, there had to be a core. How big it was up for debate. You're right, the lack of a magnetic field and the fact that it's rotating at about the same rotation rate as Earth, you know, some people have argued that, well, you know, Venus has no magnetic field because it's rotating so slowly and so forth. But In fact, the density is so low that this thing has to be like an iron sulfur alloy, which has a really low melting temperature. So the idea that it could not be solid is, or the idea that it could be solid, it would like be way too low of a temperature. That said, the dynamo modeling people are looking into that. And I think there's no evidence for an inner core. And at least on Earth's core, it's not so much thermal convection as it is compositional, as essentially the iron liquid alloy is the iron is settling out toward the center that's actually providing most of the buoyancy driving the dynamo, more so than the temperature. So maybe Mars is in that regime where there's no, not yet cold enough to crystallize out material, because it's at a lot lower pressure. So it's a very different regime than Earth's regime.
So that's wild what you just said. So when I was a grad student many, many years ago, at least what I got out of my work when I looked at this then was that Mars was cooler off, right? No magnetic field, no liquid core, it was cooler. You're saying it's, and that was thought because it was further out from the sun. But you're saying it's actually a warmer core, right? It hasn't cooled off as much as the Earth.
No, it's definitely cooler than the Earth, but the pressure regime is so much lower that the melting curve, you know, which is a function of both pressure and temperature, you have to look at, and composition, because there is so much of this light sulfur element, and that, you know, the melting temperature of pure iron at Mars conditions would be about 2000 Kelvin. The melting temperature with as much sulfur as people thinks in it is like 1200.
Wow.
So it's like, it really is pulling the melting point down.
Okay, this makes sense. That's fascinating.
But yeah, it's different, and it's creating some interesting interaction. I'm hoping that it will interact with the group at Johns Hopkins, which is doing the dynamo modeling, because we can kind of provide them with some constraints from the mantle on temperature.
Okay, thanks for that.
Sure.
Any other questions around?
Okay.
But yeah, otherwise, thanks everybody for joining us. Again, we've got our last one of the semester, our last seminar of the semester will be on December 1st, so 2 weeks from today. It is a little bit awkward because we have the Thanksgiving break holiday kind of in the middle, so it seems it'll be a lot shorter because we'll all be kind of enjoying the holiday next week. But otherwise, and I guess I should say, I don't have anybody to fill for that spot for now. So anybody that would like to present, feel free. Again, the only constraint is it's something that roughly is something, you know, space related. So please contact me if you are interested. But thanks everybody otherwise, and we'll see you either in 2 weeks, or if not, maybe in the new year. So thanks so much.
Thank all of you, and thanks, Scott. That was fun.
Great. Glad to be able to share.